Hi, my name is Josh, and this is Signal Drift, where we take an intuitive and unscripted approach to DIY electronics. Today I wanted to talk about a megahertz class homebrew function generator. A function generator is a circuit that can generate arbitrary waveforms at arbitrary frequencies. There's always a limit to how high you can go in terms of your frequencies. In my last video, my limit was well below a megahertz. We really couldn't get very high because we were using just an arbitrary timer to trigger a sample and send it off to the GPIO pins. In this video, what I'm going to be doing is driving our hardware to the limit. What I've got here is my custom Raspberry Pi Pico. This is an RP2350, so it's the latest version. It's the Raspberry Pi Pico 2. It's a custom board, and because it's a custom board, I can do a fun little thing with it. I can put my R2R DAC ladder with its 8 digital pins here. I can put it right up against the side of the pinout of here because I have 10 contiguous GPIO pins. One of the reasons I chose this particular thing is for very high speed operation. There are no active components in here. It is just a bunch of resistors. This is designed for speed. If you do the math, I should be able to get a 75 megahertz function generated out of this setup. That's actually pretty high. I don't expect 75 megahertz to be terribly usable, but we should be able to operate in the realm of 20 to 30 megahertz with actually relatively good signal integrity, at least for sine wave functions. And we're going to run in some issues at these higher frequencies and we'll talk through that. But here I'm just learning how the R2R DAC ladder works, the basics of a digital to audio conversion, and how fast I can make this simple little setup move. I really just wanted to test the limits of what we can do here. So with the Raspberry Pi Pico, it has what's called a programmable I/O block, and it's got 3 of them. They're little tiny, basically coprocessors that all they do is take data from memory and they shovel it out the GPIO ports, and they can do this as fast as the system clock. So if the system clock ticks 150 million times a second, they can shovel out 150 million samples a second on the GPIO ports. And if we do the math with a conservative overclock for the Raspberry Pi Pico 2 of 300 megahertz, very, very doable, we should be able to get up to about 75 megahertz in terms of arbitrary function generation. First, I wanted to talk a little bit about the DAC ladder that we're using. This is our DAC ladder, and I'm just going to explode it a little bit here. It's got a ground pin, and it's got an out pin, and then it's got 8 input pins, and we tie these to the GPIO pins. So we have a GPIO in, we'll call this 0 through 7. And they feed 3 volts into here, into each one of these pins. If you want to take a look at the last video, I'll place it here. When you feed a 3 volt signal into one of these pins, it gets divided by 2 every step of the ladder it goes. So if I feed a 3 volt signal into this pin, it gets divided by 127 by the time it gets to the out pin. This pin gets divided by 2 by the time it gets to the out pin. So we have a perfect binary ladder for a binary input, and it produces an analog voltage out. My GPIO pins, because we've got 8 bits, they can encode 0 through 255, right? And if I place them on here, I get a matching analog output that goes from 0 to 3.3 volts. So by twiddling these bits on the DAC ladder very, very quickly, I can construct a waveform on the out pin. And the way we do this is, we take a sine wave. So if we've got a graph, we take our sine wave graph or any waveform that we want. So we can do a square wave, although this isn't a great way to do a square wave. We can do a triangle wave. We could do a sawtooth wave, but we're going to start out with a sine wave. What we do is we take a sample. If you wanted to take 8 samples, at each one of these places along the way, 0, 1, 2, and 7, we take a sample of our waveform, and this creates a lookup table. At 0, we're going to have 0. At 1, we're going to have some intermediate voltage. But we scale this up to 255. So we say, we arbitrarily call this 255. And down here is 0. So by breaking our sine wave up into 8 samples, we create a lookup table that we can use to represent a digitized version of this sine wave. But it's not very granular. It only has 8 samples. We could do more samples. We could do 128, we could do 256, but one of the problems is if we want to go to higher frequencies, we're going to be playing back one of these samples every tick of the clock. If I had 8 samples to represent every waveform that I wanted to generate, and my CPU is, say, running at 100 megahertz, and I have 8 samples, if I divide by 8, that gets me down to 12.5 megahertz, right? This is one way I can control frequency generation. So if I have a fixed frequency of my CPU, I can just sample a sine wave, right? And then I can play the numbers that are associated with each one of these on each cycle of the CPU out of the GPIO ports and then reconstruct that actual sine wave as a real voltage, right? One approach I could take is just to change the frequency of the CPU, and actually this kind of works. So I could say reverse the math here. So if I wanted a particular output frequency, I could solve for the CPU frequency that I needed. Yeah, so our CPU frequency equals the target times 8. So if I wanted to say 10 megahertz output, I would multiply it by 8 and I run the CPU at 80 megahertz. And this will work for some values of CPU frequency. Unfortunately, with the Raspberry Pi Pico, you can't set any arbitrary CPU frequency. You could set it close-ish, probably close enough that you wouldn't really notice that your frequency isn't exactly what you want, but okay. I don't love that as a solution, and I don't love having to figure out what values are close enough. It's a non-trivial task. The other thing we could do is, since we're using programmable I/O, the programmable I/O blocks are little coprocessors that run at their own clock rate. And by default, they run at the clock rate of the CPU. You can run them at a different clock rate. So you could clock the programmable I/O units at a different frequency as well. I tried that out. It works better because you can hit any arbitrary frequency that you want, better than the CPU, but it introduces some weird jitter. The problem with clocking PIO in that way is that if there's a fractional divider, it either has to run in a CPU clock cycle or not run in a CPU clock cycle. So it will kind of dither things over time if there isn't an exact match. In other words, if it can't run every other cycle or every 4th cycle, it might be in between those two. So it'll run every 2 cycles every once in a while, every 3 cycles every once in a while. And this introduces a lot of jitter, which you would see on the output waveform. So you really don't want to do that PIO clock divider because it leads to jitter. So what's a better approach? A phase accumulator. What a phase accumulator does is it reconciles the mismatch between your sample rate and the rate at which your frequency would naturally want to play out on the CPU. Let me give you an example. Suppose I have a 100 megahertz clock and I want to play a 10 megahertz frequency. So to fit this in, I need to repeat this 10 million times a second, where my clock is going 100 million times a second, right? So if I do that division, that means I have 10 cycles per waveform. That's great if I've created a 10 sample waveform to play. But no, usually I have a fixed waveform and it's usually a power of 2. So let's imagine I have a 8 sample waveform. Remember, like this. We've created 8 numbers that basically represent a digitized sine wave. Well, I've got a mismatch between this 8 and this 10. If I want to play a 10 megahertz tone, every 10 cycles I've got to repeat myself. I've got to wrap all the way back around to where I started. It tracks the difference between this 8 cycle and 10 cycle mismatch. So it is the magic of this phase accumulator that you're constantly running behind the scenes that's perfectly accurate, that you're rounding down to one of your samples, that allows you to spread out your mismatched samples across more CPU cycles. This is how we keep a fixed clock and spread our fixed waveform samples, 8 or 128 samples per waveform, across the CPU cycles to target a particular frequency output. One of the other things I wanted to talk about is how we get the screamingly fastest performance out of this. In the last version, what I used was called a timer interrupt. And these are microsecond levels. So this means approximately 1 megahertz sample rate. If you have 4 samples per waveform, that's going to get you 250 kilohertz, which is not terribly high, and we're running up against the limit of what a Raspberry Pi Pico can do with interrupts. Dispatching 1,000,000 interrupts a second is very CPU intensive. It's just incredibly inefficient to do it that way. What we need to do is pre-calculate a buffer that holds all the samples that we're going to send to our PIO hardware and use something called direct memory access, or DMA. And DMA is, again, just like another coprocessor inside the Raspberry Pi Pico that allows you to stream data directly from memory to the PIO hardware with 0 CPU intervention. Now, the beauty of the Raspberry Pi Pico is that it can operate all of this at the full speed of the processor. So DMA can keep this PIO block fed with enough data that it can output a sample per clock of the CPU. So 300 megahertz we're talking about is about the max of what I'm going to comfortably overclock this Raspberry Pi Pico 2. That with a 4 sample waveform will give me 75 megahertz output. So that's the theory, at least. In practice, it's a little complicated, and it took quite a lot of work for me to get to this place. We got some initialization code here. Mostly it just does the overclock. We set the overclock and we overvolt the CPU a little bit. We have to generate our lookup table. So here we have a sine function. So remember, we have this table length, which is associated with the max table length. So it's 128 samples per waveform. So we digitize a sine wave into 128 samples. This is just a loop. It calculates the sine wave value at each of those 128 positions along there. So that's equivalent to this, but with many, many more samples. And then we got some examples for a triangle table and a square wave, which is trivial. You don't want to use a DAC to generate a square wave. Every single one of these pins can generate very, very high speed square waves. There's no reason to use a DAC. I'll show you what happens when you do it, but it's just not nice. So the flow of this program is simply that we set the frequency at the top. We generate our lookup table, our sample table for the function that we want to output. We initialize our PIO block. We fill our DMA buffer, and we're going to take a look at this. I'm not going to walk through this in a huge amount of detail, but this is that phase increment that we were talking about. And then we also have the phase accumulator that handles the mismatch between the native frequency. Remember, we're not ever changing the frequency of the PIO block or the CPU. We're always just changing the frequency that we want to output at. So what this phase accumulator does is it handles that mismatch between them. The fill DMA buffer calculates the actual length of that buffer that gets me a number of samples that repeats itself. So it will keep going until it detects that it finds a repeat and says, okay, this buffer is long enough. I can play this buffer in a loop and there won't be a discontinuity between the beginning and the end of it. And then it sends that length off to the DMA. So let's see this in practice. It's already generating a waveform, and we can tell that it's 2 megahertz. So we're already well above where we were with our previous version of this code, just using timer interrupts. The circuit here is just trivial. So I've got a capacitor here that gets rid of the DC offset. It AC couples it and gets rid of that DC offset. It gets centered eventually, and so you can see here that I've got a 2 megahertz sine wave, and it is 2.8 volts peak to peak. That's actually pretty good. I would expect 3 volts, but what we're running into here is a little bit of attenuation. Let's go ahead and, pop a couple wheelies here. Let's go ahead and generate a triangle table. So this is just we're filling up those 128 samples with a different arbitrary function. There. And so we have a nice triangle wave. And then I just wanted to show you, again, for completeness, what happens when you try and generate a square wave. You don't want to use a DAC to generate a square wave. You just don't. Because I can show you a better square wave. I'm inputting it into the DAC. It's right there. That's the most significant bit that I'm sending into the DAC right now. So that's almost a perfect square wave with a little bit of ringing, and this is the output of that. You just don't want to do it that way. Let's stretch our legs a little. Let's go up to 5 megahertz and see what we can do. And we have a fairly nice 5 megahertz sine wave, but you can see we're getting significant attenuation, but we've still got a lot of headroom. We can go quite a bit higher. So let's go up to 10 megahertz. You're starting to see a good amount of attenuation here, but we still have a pretty stable frequency. So this is the cool bit about the little algorithm that I put together with a phase accumulator, is it locks on to a frequency very well and very accurately. Let's go ahead and say like 10.1. Let's see what that does. How accurate is that? There we go, 10.11 megahertz. It's probably to a part in 100 or a part in 1,000 accuracy. So let's go a little bit higher. Let's try 20 megahertz. You can start to see we've definitely reached the our scope can't go down anymore in terms of its time divisions. It's doing a relatively good job, and it's actually reporting the frequency well. Let's go ahead and look at a better desktop scope. So this scope is doing a much better job. So we've got a 20 megahertz sine wave. Looks pretty good. Let's try out the triangle wave and see if it's any different. It looks a little pointier, but what we're seeing here is that, anything with a sharp point actually has a relatively high frequency component in the frequency domain. That will get attenuated. So anything with a high frequency component is going to get attenuated and kind of rounded over. So that sharp pointy bit in the triangle wave gets rounded over, and this actually looks more like a sine wave. And even higher frequencies, sine wave and a triangle wave, are just going to be almost indistinguishable. Let's go higher. Let's go up to 30 megahertz. Here again, you see we've got good accuracy. We're at 30 megahertz. We've got actually, it looks like a little bit nicer sine wave. As we get higher up in frequencies, just kind of the natural smoothing gets rid of all those higher frequency components and leaves an almost pure sine wave behind. But we're significantly attenuated now. We're at about 1/2 of a volt peak to peak. Let's go for 50 megahertz. I mean, that looks great. Let's go up to 60 megahertz and see what we get. There we go. If we zoom in a little bit, you can see a little bit more of that jitter that I was talking about. And that's just inherent because there is a mismatch between the sample frequency and the clock frequency that we're kind of papering over and averaging over in the time domain. You're going to see that jitter here. Well, there's no way we can perfectly play a 60 megahertz frequency at 300 megahertz. And I think we could make this even worse if, say, we do 61 megahertz. That would give us a nice mismatch. This is almost unavoidable. At least I haven't found a good way to avoid it. And it happens more at higher frequencies because we're running out of time to do our work. And, natively, there's only about, if we're trying to do 60 megahertz, we got to get that in like 5 cycles-ish. 75 megahertz would be 4 cycles of the CPU. So this is between 4 and 5, I think. So, and it's non-integer divider of that. So the samples that we're sending out are kind of switching between 4 and 5 to average out to 61. Let's go for gold here. Our theoretical maximum output is 75 megahertz. Let's see what we can get. And this should be a relatively smooth waveform because it is a perfect divider of the base frequency of the CPU. And you can see we're down to about 1/4 of a volt peak to peak. So really significant attenuation, but the signal is still strong. I mean, there's not a lot of noise on it. There is some inherent jitter here, although if we zoom out, it looks a little bit better. We're doing it. Our signal generator is ripping out 75 megahertz. That's awesome. So let's go ahead and see, what's the triangle wave look like here? Am I going to be right? Is it going to look exactly like the sine wave? It does. It looks almost exactly like a sine wave. Can we go higher? Sure, let's try it. Try 100 megahertz. Let's just see what happens. I don't think anything good. I think our algorithm will try. So it's getting significantly attenuated. I'm frankly surprised that this worked. I didn't test the latest version of this algorithm. I went around for days on this code trying to perfect getting a really stable frequency output, and I had no idea this could do 100 megahertz stable like this. It's fascinating. I'm pretty sure it can't do 120. Let's see what happens. It's trying. Oh, there we go. Now we're falling apart. Let's go for 150. I mean, because that's another multiple, but I think it's impossible that we could hit this. I'm not exactly sure how we're hitting 150 megahertz. That's fascinating. Now, we're pretty heavily attenuated, so it's looking quite messy, and we're down to almost 100 millivolts peak to peak, so we're attenuated about 30 times from our base voltage that we saw at like 500 kilohertz. I'm fascinated. It's doing a stable 150 megahertz. Wow. I can't choose arbitrary frequencies around there. I'm sure if like I did 149, it would fall apart, or at least it wouldn't be accurate. But it's just amazing to me that I'm able to do 150 megahertz on a CPU that's clocked at 300 megahertz. So now I want to talk through an application of an arbitrary function generator. I can generate frequencies at an arbitrary frequency, and I can modulate them. And here's a little bit of a hint here. I have picked a frequency that's 1700. You might have noticed that on the AM talk radio dial if you still partake. That is an AM radio frequency. It's one of the better ones that I found around here to be able to transmit on, and I can turn my Raspberry Pi Pico into the world's worst radio transmitter. It's horrible. I don't think the FCC is ever going to knock on my door about this, because if I pull the radio away just a couple feet, you can't hear a darn thing. So the idea is that we save off the full amplitude DMA buffer, and then once every audio cycle, and so we have an 8 kilohertz audio signal, I saved off my Beethoven's Fifth sample as an 8 kilohertz PCM, and we can take a look at that. This is da-da-da-dum.h, and you can see the wave table is just a whole bunch of 8-bit numbers. Those represent the amplitude that was recorded or sampled from the recording that I did. And so this is significantly downsampled. It came from a very high quality recording. I sampled it down to 8 kilohertz because AM radio, 8 kilohertz is probably even too much for the fidelity of AM radio. AM radio is really, really crappy, and a higher frequency sample would introduce a static and noise. So it calls this timer IRQ handler 8,000 times a second, and the biggest thing that it does is it just amplifies our DMA buffer. It reads in the next byte of the waveform, the recorded waveform, as the amplitude, and then amplifies that DMA buffer with that amplitude value. We're just updating the waveform every 125 microseconds to encode the amplitude of the audio sample that we have. So let's go ahead and see what that looks like on the oscilloscope. I can almost hear it myself because I've been listening to this. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. So you can see the amplitude is modulating in response to Beethoven's Fifth. And it is doing it at 1.7 megahertz, which is on the AM dial. What happens if I take my radio, got a little radio here, and turn it on? Radio mode. Let's see. I mean, we're a foot away from the Raspberry Pi Pico. You can see, you can hear there's just nothing but static. You can see that far away, a couple feet away, we're not really getting much of anything, but as I get closer, you can hear it. There we go. It's not bad. I mean, it's not good, but it's not bad. And there you go. I am bit banging a homebrew DAC at 1.7 megahertz, amplitude modulating it at 8 kilohertz to create a really hacky radio frequency that my radio can pick up an inch away. So I don't think the FCC will be knocking down my door anytime soon. But isn't this cool? This is very, very cool. I love it. This has been a really cool exploration for me. I've had about a week's worth of time kind of diving into this and perfecting these various algorithms. The algorithm that surprisingly, I've still got to go back and do the math, took me up to 150 megahertz. I thought I would top out at 75 megahertz. So I need to go back and look at how I got to 150 megahertz. It makes no sense to me. But it's been a really cool exploration in trying to push this hardware to the very bleeding edge. I think this was plenty fast enough, and it maxed out at 150 megahertz, which was super surprising to me. Although I would not call that like a general purpose usable frequency. I would say the effective top frequency of this as a usable signal generator would probably be somewhere around 50 megahertz, maybe 40 megahertz, something like that, where you could confidently adjust and hope to hit your target frequency pretty accurately without a lot of jitter, which is really good for such crappy hardware. Well, thank you for watching to the end. Again, my name is Josh, and this has been Signal Drift.